I do this the first question.
Okay, good afternoon, everybody. We're going to start today an important topic for your series, and from now on, we're going to have very important topics, and we'll be involved in math a lot, especially integration. But don't worry, for about the integration, I'm going to give you like a sheet that has integration table that you're going to use. I will never ask you in this course to do like hard integration like sine square times ln over x squared, all these things. No, just the main thing, the concept. And if you need any integration, I'm going to give you the sheet and just you apply, and you'll see how we'll do that. But also in the lab, it will be very important when you apply all what you are going to learn in the lab using MATLAB. It will make you understand the topic deeply. So for your series, and since all the topics from now on is going to be like, as I said, math involved, but I'm going to tell you about the application before we do the math. So for your series, what's for your series and why we need it? What are the application? Did you have any idea about Fourier series before in math? Did you study math for your series? Did you read it?
Never heard of the word.
You never heard, okay. Did you know about Fourier himself?
That's a guy?
That's a guy, yes.
Well, no.
Yeah, you'll like him, I mean, after we have. So that's, I mean, what we're going to talk about. We're going to talk about what's Fourier series, why we need it, and we're going to study the two forms of Fourier series. One called trigonometric Fourier series and the other one complex exponential series. And then the line spectrum, which is really important. Okay, so why we need Fourier series at the beginning? Why? What do we need? Well, let me just give you a quick example. You remember when you had circuit? Did you have circuit 1, circuit 2?
I'm taking that right now.
All right. In circuit 2, you will have like sinusoidal or AC system. It means the source is AC. In circuit 1, you focus on DC as input, and then in circuit 2, you will focus on AC, especially sinusoidal, because the all electric sources we have, like we have here in the wall, it's sinusoidal. So it's very easy. You are going to use something called phasor diagram or phasor quantities, and it'd be easy to analyze any system. The input is pure sinusoid. That's easy. There is, I mean, a direct way to do it when the input is sinusoid. But the question is every source sinusoidal? No. For example, you have a periodic function here, input. It's not sinusoidal. It is sawtooth. To do the analysis for the circuit like that, it's headache, because you have to define this function in time, and you repeat it, and it just is very hard. However, if it was sinusoidal and periodic, you don't have to do it all just one period, and then you apply it, and that's it. You get the general solution. So they thought about it. This nice guy, Fourier, he said, okay, what about if we can decompose the signal, the input signal that, for example, this one sawtooth, we make it like, I mean, consist of many sinusoidal with different frequencies. And how we found this, any signal, whatever the shape of it, you can, and it's periodic, you can decompose it into many, infinite number of sinusoidal, but with different frequencies. I did, I mean, when I studied that, I did, something by MATLAB. It was very interesting. I did a program, and I wrote to you here when I was a student. Where is the program? Okay, let me show you what I did. I want to make sure that this is true. So what I did, I said, okay, they told me that any signal consists of many. Okay, so I got the MATLAB and I said, okay, I'm going to have like a sine wave with frequency, whatever the frequency, let's say 50 hertz, 60 hertz. And then I got another one like has the 3 times the frequency. So during this period, I did like 1, 2, 3. Because usually the main frequency, they call it fundamental component or fundamental frequency. And by the way, using music, they call it harmonics. So this is the fundamental component or the first component. They call it the fundamental component. And the frequency of this signal, you can call it, for example, omega naught as the fundamental. If you express it, or you can say F naught, doesn't matter, F naught in hertz or radian per second. Then this one, in the same period of this fundamental, I did 3 cycles. See, that's 1, 2, 3. So the frequency of this component 3 times the fundamental. So we call it third harmonic. And the musician use this, I mean, the concept in their notes. And then you can do like 5 times, 1, 2, 3, 4, 5. It's split over the same period. That would be the 5th harmonic. I did it. I entered input to the MATLAB, and then I asked him to sum these signals together with different amplitude. So I got something like that. And it's repeated. It's not pure sinusoidal. It's like there's disturbance. That was the result. Almost a square wave. And when I changed the amplitude of the 3rd, the 5th, the 7th, I'm getting different shapes and periodic. So it was true, yes. Any signal can be decomposed into sinusoidal component with different frequencies, and all components are referred to the fundamental frequency, the first one you get. You call it fundamental. If you got 50 hertz, so your F naught equal 50. You got the first one 10 hertz, then it'll be like the fundamental equal 10 hertz. And the rest will be referred to a multiple of this frequency. 3 times, 2 times, 4 times, whatever, till infinity. Even the square wave, it's a periodic function. You can make it consist of, but should be symmetric. You can decompose it into sinusoidal. For example, I can tell you that the fundamental component of this square wave, the frequency will be the same as the frequency of the square wave. It will be like that, the fundamental component, something like that. And then, of course, if you add things, then other components with different frequency, you can get it like almost square. Every time you take more components, you get very close to the square wave, straight lines. You get less, so the square wave is not really regular square wave. So that's the whole idea of the Fourier series. So what, when they decompose into components like that, that will be easy, because I just said in circuit analysis, when you have sinusoidal input, it is really easy to analyze the system. Very easy to find the current, the voltage. Just you look for the amplitude and the frequency and just do it. Easy. But what you'll do it like many times. If you have 3 components, you will apply the same technique 3 times. Each time will have different frequency, different amplitude. That's it. But if you are using the original signal, that's a headache, and sometimes impossible. So that's, I mean, the value of Fourier series. And I already explained the harmonics. The harmonics, when you have irregularity in the signal, like you see these parts, that's a pure sine. Doesn't have any harmonics. It's just it's sine wave. It's one component, fundamental component. That's it. But when you have something like that, it means there is something else added to that main component. And that's, by the way, not abnormal. It's normal. Because, I mean, we don't live in the perfect world. There are many disturbance, electromagnetic wave thing added to it. So it causes all this irregularity in the in the current or the voltage. That's why we consider this non-sinusoidal. And then we'll decompose into sinusoidal component. Okay. I'm going to download or upload the Folio system with this files because it's interesting if you can do the MATLAB. I have the program here. If you want to check it, you can change the frequency, just play with it. And even I did something interesting. When I was playing with the frequencies and adding, and then I have like a function in MATLAB, I can listen to the tone, to the sound. So it gives you a different tone. When you play in the frequencies and you add it like that, then you can hear different tone. Okay. And I did like practice if you wish to apply it, and that would be fine. So Fourier series, it's a mathematical tool to represent periodic signal, non-sinusoidal, to sinusoidal component. To why? To simplify the analysis of circuit. To work with Fourier series, you need to have background in complex variables, complex numbers, and integration. And that's what we did. That's why we did the revision for the complex variable to make sure. And I have also here, I mean, this whatever I explained, I put it again in the notes. So I mean, you can review the complex if you wish. That's for revision, and that's the old function that you use in complex. And I have some YouTube. You can, if you want to, if you are stuck with complex again, you want to review. I put it there for. Now here you go. That's the Fourier series. X of t, that's the signal, which is periodic and non-sinusoidal, like square wave, sawtooth, anything. That's X of t. I wish to express it in this way. Let's look at every component. A naught. A naught, it's a constant term and represent the DC component in the signal itself. It could be zero, it could be non-zero. So A naught represents the DC, the average. How you know the DC? That's why, I mean, there was time, I think in some exercise, I asked to find the average, the signal. I was just preparing you for your average signal, it means DC component. Let me explain why. I have space. Okay, I have space. So if you have signal like that, pure sine wave, and you have 5 minus 5, the maximum 5, the minimum minus 5. So, and you find the area and the average funds equal 0. Why? Because this area, the positive area, equal the negative area. When you add them to divide it by the period t, your funds equal 0. What does it mean? It means there is no DC component in this one. If you analyze it, no DC component. But what about if you have something like that? Sine wave, pure sine wave, but that's like, say, 8. Okay. And that's negative 2. Now there's an average. How you find the average? The average, you find the area and the area here, and you subtract and divide it by the period t. Let's say that the period is equal 2 seconds. And that's the same thing, 2 seconds. When you do here, you'll find that the average or the area itself is equal 0. The total area is equal 0. But the positive and negative. Here, the area is bigger than that. But I can tell you how you do for some sine wave like that. It's a kind of hard. You have to make integration. But if it was a square wave, let me do that just to make it simple. That's 8 and that's negative 2, and the period is equal. Let's make it like 4 seconds. So it means 2 seconds here, 4. So that's 2 seconds. So the positive area, it's equal 8 times 2. That's equal 16. And the negative area, the height is equal 2, and 2 would be 4, right? So the area is equal 4. When you subtract, you get the area, total area, equal 16 minus 4 is equal 12. So the area is equal 12. Then divided by the period, which is 4 seconds, you get 3. So the average is 3. What does it mean? It means that this signal, when it was symmetric, I added DC components, DC source equal 3, so it left everything up. If you got the 3 out, what you'll get from this signal? If you got 3 out, you'll have 5 in the top, and you add the 3 there, be -5. Be symmetric, no DC. So when you have pure sinusoidal, you can do the integration. I'm not sure how to do the integration, but I can tell you, if I add, because it's symmetric, 8 and -2 is equal 6, divided by 2 is equal 3, so it's 3. If I subtract 3, it means it was 5 and minus 5, this one, and then I added 3, it lifts it up. But how to find the average by the area means integration. That's why when you look for A naught here, how to find, you integrate the signal from 0 to t over one period and then divide by the period. So the integration here gives you the area. And then divided by the period t, it gives you the average, which the physical meaning DC component. Okay. Now look for AK, and what's AK and BK? And A naught, what do you call them in Fourier series? You call it coefficients, the coefficient of Fourier series. And by the way, this is applicable only for continuous time signal. Well, so what's AK? Well, look at AK, the coefficient of cosine. Like you try to say that this signal I can represent by A naught constant, like 5 plus 3 cosine. Let me write some example. Like you might find something like that. X of t is equal to 4 plus 3 sine 10t plus 2 sine 30t plus 4 cosine 10t plus 1.5 sine 30t. What is that? All these are the components of the signal itself after I did the Fourier series. Let's explain what does it mean every term. 4 is the average. That's the DC component in the signal. 3 sine 10t, that's the minimum frequency. I mean, yes, the minimum frequency. Okay, so I say this is the fundamental component, and it's sinusoidal, and the omega it's equal 10, because sine omega t, so omega is equal 10 radian per second, and the height is equal 3. That's the first component. Second component is the third harmonic. Why am I going to say third harmonic? Because that's 30, and 30 is 3 times the fundamental component, which is 10. Because I can, this is omega naught, is equal 10 when you look at it. And this one, 30, that will be omega 3, was equal 3 times 10. Yes.
So the 3 sine 10t, that was amplitude of 3 of the first?
Yes, the amplitude of the first, or you can say the fundamental component. That's right, the first component called fundamental component. And then you got the third harmonic, sine 30t, and the height is equal 2. And you have another fundamental component, cosine 10t, and the height is equal 4. And you have another third harmonic, it should be cosine 1.5t. In general, you have sine terms, cosine terms. Of course, by math, you can combine sine 10t and cosine 10t in one term, and will be like cosine 10t plus shift. We're going to do that later, but I'm just telling you, I'm trying to explain to you what does it mean, the main formula for Fourier series. So that's what you're going to get. 3, 2, 4, 1.5, they are called coefficients of Fourier series. 3 and 2, they are coefficient of sine terms. They called AK. How did they define it? They multiply the signal by cosine, k, omega naught t, and k are integer. What does it mean? Look at that. If omega naught in this example I'm giving you is equal to 10, t, k could be 1, 2, 3, 4, 5. If you put 1, you have the fundamental, 10t. If you put 3, it will be 30t, it will be the third harmonic. If you put 2, it will be 20, it will be the second harmonic, and so on. So that's why they put k here. So you have to multiply x of t by the cosine k omega naught t, and you integrate it over one period. And you divide it by the period like the average, but multiplied by 2. So AK, the coefficient of sine terms of Fourier series. BK will be the coefficient of cosine terms in Fourier series, but you multiply by sine. All right. So you have here term, cosine terms, we call it cosine term, sine term. Cosine term, the coefficient is called AK. Sine terms, the coefficient called VK. Most textbooks are using this notation A and B. A for cosine and B. How do you find A? This is the integration. How you find B? And then you put it there, you plug it there, and then you make the series. So that will be the equivalent components of signal x of t, which is periodic. Yes.
So it would be cosine 1 of like the k would be 1, right? And then the
Cosine t, yeah, that will be great. That will be A1. That's good, you see. And 1.5 will be A3. Right? Because it's multiplied by cosine 30t, cosine 3 omega naught. It means k is equal 3. All right. You still have k here also. And sine 10t, when you look at sine, you have b. And this is your first component, that's omega naught. So that's the first one, A1. And 30, that will be 3 omega. That's the third harmonic. So that will be equal A3. So in general, you can say that x of t equal A naught, the average. Now, we start by A. A1 is multiplied by cosine. Cosine, you put here k equal 1. We're talking about 1. So equal 1, what? Omega naught t plus A2 cosine t omega naught t plus A3 cosine 3 omega naught t. And you continue. Then you start B1. B1 will be the same. Sine omega naught t plus B2 sine 2 omega naught t plus B3 sine 3 omega naught t. And you could, that's it. So that, I mean, that is the meaning of the sum formula that's given for your series. The average, cosine terms, sine terms, and you add them. The thing that we observe when we do Fourier series, we found every time we are increasing the frequency, like after 5th or 7th, the amplitude is decreasing. Like A1 is the highest, then you got A2 smaller, A3 smaller. So every time you are moving with the high frequency, found that the amplitude is smaller. So that's why sometimes we ignore the high harmonics, the high frequency harmonics, because it'd be like 0.1, like 1% of the fundamental. The question is how to find A1, A2, A3, how to find B1, B2, B3. That's the formula. That's how you find A, K in general. And the answer will be in terms of K. BK, the same thing. Why wouldn't do example? Just to easy example and just to go through. But of course, there are, I mean, conditions you can apply for each series not to any function. Should be limited, not going to infinity. There is a limit, maximum, minimum, somewhere. It doesn't have discontinuity everywhere. Maybe you have discontinuity in 1 point, 2 points, but not everywhere. That will be hard. We're not going to this issue. Okay, that's, I mean, that's a signal, square wave. And we like to find the components. That's the way it's defined mathematically over one period. First of all, we got to know what is the period of this. So you can say that the period starts from -1 to 1 and then be repeated all the time. So the period T is equal to 2, right? 2 seconds. Start from -1 up Yeah, and then it will be repeated again, the same thing. So the period will be like equal to 2 seconds, right? Well, we need to find what the first thing you do. We need to find, yes.
Okay. Were you asking what the first thing you need to do?
Yeah.
That's the average value, right?
Yes, the average value. So the average value A naught, the equation of A naught is 1 over T, the integration over 1 period. By the way, you can choose where you are going to integrate. You can choose any from 0 to 1, from -1 to whatever you want to do. You can, what I'm trying to say, the period is equal T, 2 seconds. So you can integrate from 0 to 2 or from -1 to 1, whatever you like. All right. So let me do from -1, because I mean, I just want you to, because I mean, here I wrote from 0 to 2 to T, it means that you got to start from 0. No, the integration over 1 period. So, and you choose the easy one for you. Okay. So when I look at it, for this example, you can start from 0 up to 2, but it'll be like it's changing. But I mean, from -1 to 1, let me just write the expression x of t dt. That's the equation. So t is equal to, and the integration should be, I can say from -1 to 1 over this period, and x of t dt. Now, I will say 1 over 2. When I go from -1 to 1, I find from -1 to -0.5 is equal 0. So ignore it. So actually, I start from -0.5, right? And then it will continue, and then again up to 0.5, and from 0.5 to 1 will be equal 0. So actually, my integration will be from -0.5 to 5. That's why I choose that one. But if you choose from 0 to 2, you will find yourself, you have integration here plus another integration here. But here I have only one integration. And you know our issue, save the time. The exam is just fast like that. So I will say from -0.5 to 0.5. And what is the value? Of course, I'm choosing easy one, so I won't be involved in math. I want to understand the concept. It's 1. So I say 1 dt. When you have function here like exponential, something like that, as I said, promise you, I'm going to give you a table. Just to look at the table, put the formula, substitute. So 1 over 2, what is the integration of 1? T. And the limit of integration from -0.5 to 0.5 equal 1/2. And t 0.5 minus -0.5. So it will be equal to 2 times 1, which is equal to 1. 1 times half is equal half. So this signal has a DC component equal half. And by the way, I could do it without integration, but just I want to apply the integration so you know what you do if you don't have an easy function. But when I look at it like that, you got 1, and this one I'm going to spread over 2. So the area is equal 1, right? That's equal 1. The height's equal 1. 1 times 1, the area is equal 1. I want to spread over the. It means it's going to be like that. So if you continue, that's the DC component, half. It has half size. Okay. Now I want to find the coefficient of. Yes, you have question. Question. Okay. Now I want to get the coefficient AK. AK, it's the coefficient of cosine terms. How I get it? I multiply by cosine, and then I integrate over 1 period, and multiply by 2 over t. Okay, let me just write the formula now. So now we have AK equal 2 over t, the integration 0 to t, xt multiplied by cosine k omega naught t dt. So in this formula, obviously you need always to find omega naught. How you find omega naught? The fundamental component. Yes, we have the t, the period, right? We have t. I just got this new software. I tried on PDF, so I like it. So I'm not very familiar with it. So now the period t is equal to 2 seconds, and omega naught is equal to 2 pi over t. So equal 2 pi over 2 pi. So omega naught is equal pi. So now I'm going to substitute 2, and the period is equal to from 0 to 2 x of t cosine k, I leave it as it is, omega naught is equal pi t dt. Well, so 2 over 2 is equal 1. Now I look from 0 to 2, from 0 up to 2. Well, from 0 to point, I break it into 3 periods, from 0 to 0.5, from 0.5 to 1.5, and from 1.5 to 2. The one in the middle is equal 0, so I have 2 integration from 0 to 0.5 and from 1.5 to 2. All right, so I will say I will have 2 integration from 0 to 0.5 and from 1.5 to 2. And xt was equal 1. So 1 cosine k pi t dt. The second one also was 1. What's that? Okay, saved. 1 time cosine k pi t dt. Okay, now I'll do the integration. The integration of cosine is what? Yes.
So for the AK part, that's always going to start at 0.
Yeah. Yes. Yeah. Now I will make the integration. What the integration of cosine? The integration of cosine, anything x, for example. No, don't write x. Integration of cosine theta d theta is equal what? Sine theta, right? But if you have any constant here like a, you have divided by a, right? That will be the integration. All right. So the integration of cosine is equal sine whatever inside k pi t over whatever in the front of t, because I'm integrating with respect to dt. So divided by k pi. And the limit of integration 0.5 plus the other one 1.5 2. The same thing, sine k pi t over k pi. Oh, that's it. So then that's the result of the integration. And the limit from 1.5 to 2. All right. Now we're going to substitute, but obviously k pi on the bottom is common, so I'll take it. Yes.
The integration of cosine negative sign?
Well, I mean, to check that, I used that when I was saying it's negative also. So you differentiate. What definition of sign? That's it.
Oh,
You don't have any negative sign.
okay.
Yeah.
So why is it from 0 to 0.5 and 1.5 to 2?
I just said because it's 0 between. No, from 0.5 to 1.5 is equal 0.
Okay, so we're still doing a full period.
Of course, will be. But I mean, I'm not going to get the 0.
I just didn't know why we changed it. Okay, gotcha.
Now I will take 1 over k pi as a common factor. And then you have, I will do 1 by 1. Sine k pi t, 1 time is equal 0.5. So I'll have sine I put k, not k, I put t, by the way, t, half. So I have k pi over 2 minus sine 0. That's the first one. The second one, 1 over k pi sine. I put t equal 2. So I have 2 pi k minus sine 1.5. For t, it will be 3 over 2 pi k. Okay. Check if I did any mistake. Now let's find each one. Sine 0 is equal 0. What about, let me just write here 1 over k pi, try to collect. What about sine k pi over 2? You got to try k, when k equal 1, when k equal 2, and things like that. And also to make your life easy, I'm going to give you a sheet. It tell you when you have sine k pi over 2 or sine k pi, it goes all the things in the sheet, and they'll tell you 1 is equal 0, 1 is equal 1, 1 is equal -1, so you can use it directly. But let's just do it the first one, we'll do it together. Sine k pi over 2, what is that? If you don't remember anything, just you'll say, okay, I will say when k is equal 1, you have, because you start from k equal 1, not 0. Why? Because you already got the 0 with a0, with the average. So for k, ak and bk, you start from 1, not from 0. So k equal 1, sine k pi will be sine pi over 2, which is equal to 1. When you have k equal 2, you have sine 2 pi over 2 will be sine pi, which is equal 0. So we make it 3. When you have k equal 3, we got sine 3. I'm substituting here, by the way, k here. 3 pi over 2. 3 pi over 2. That's equal -1. So obviously, when you have k even, it's equal 0. K equals 0. When it's odd, it might be 1 or -1. It will be 1 for 1, right? Let me just show you. If you have, of course, when you have k equal 4, it will equal 0. When you have k equal 5, so 5 pi over 2. 5 pi over 2, you remember that that's pi over 2. You add pi, 3 pi over 2. You add pi on this one. If you have 3 pi over 2 plus pi, put 2 and 2, so you get 5 pi over 2. This is the one. You get 1 again. So it's like, I mean, you have 1 time in the odd number 1, -1, 1, -1, and so on. Anyway, I'm just showing you what the number of it, but I mean, write sine k pi of t, and write for odd number only, even is equal 0. And then you will take care of 1 and -1. This is 0. Okay, it's done. Don't have plus sine 2 pi k. Sine 2 pi k is easy. Put k equal 1. What you get? Sine 2 pi 0. Sine 3 pi k. It always, when you have integer in front of pi, sine equals 0. Because sine has only 1 or -1 when you have over 2. But you have complete integer, it will be like, if you remember, it could be jumping from here, from this to, and it's equal 0 at this point. So so that's, I mean, equal 0. All right. Oops. Equal 0. Now we have the last term. It has 2 in the bottom. It can have things, So I'll say minus sine 3 over 2 pi k. And I'll check this one. Just next to this one. When I have k1, so you have 3 pi over 2. Sine 3 pi over 2. What's 3 pi over 2? I have -1, right? Minus. Yes, go ahead. Yeah, I'll subtract. I'm saying only this term will be -1. But we subtract to be like adding, all right, yeah. And when you put k equal 2, it will cancel 2 in the bottom, it will be 0. So it will be the opposite of this one. -1, 1, -1. So opposite. So when you say subtract 1 minus -1, you get 2. And you have this minus one, negative two. So it's either two or negative two. It's either two or negative two. So that's, I mean, the value for A of K, and it's work for odd only for both, and it'd be like it's either 2 or negative 2. 2 for what? 2 for K equal 1, and the other odd will be 3 and negative. 5, 7, 9, 11, and just you can continue like that. But of course, there are general expressions, but I don't like to show you. I mean, when I was a student, I didn't like to look at like negative 1 power 2n plus 1 over n squared, is just something like that. I'm not interested in that. I just am interested to know how you get the values, because I will ask you find the first 3 terms, 4 terms, and then you can get it. You know, it's 2 or negative 2 when this case, that case, and you know 0 when 0. So you got AK, you got A0. So what's left? BK. How you find BK? BK is the same 2 over t, the integration from 0 to t, and x of t, instead of multiplying by cosine, I multiply by sine, right? Yeah, I multiply by sine. Sine k omega naught t dt. All right. So let's continue. 2 over 2 from 0 to 2, x of t sine k omega naught, we found it's equal to pi, right? So make sure. Yes, equal to pi. Omega naught is equal to pi t dt. Great. Now, I want to integrate it again. It will be from 0 to 0.5 and then from 1.52, because it equals 0 in the spirit. Be the same thing. So I have one. So I have from 0 to 0.5, and x will be equal 1 sine k pi t dt. The second integration will be from 1.5 to 2, 1 sine k pi t dt. Okay. So why I'm skipping from 0.5 to 1.5? Why? Why?
Oh, because it's wondering.
I from 0 to 2, but now I skip from 0.5 to 1.5. I skip this.
Because there's no value.
0, yes.
Okay.
Now, let's integrate sine. Negative or positive? Well, I mean, okay, let's say you wrote cosine without sine. Then ask yourself, what's the derivative of cosine?
Negative sine.
So you have negative. K pi, and you don't have to memorize, I will just give you the table. Divided by k pi, and the integration from 0 to 0.5, plus sine k pi, oh, not sine, negative cosine, sorry. Negative cosine k pi t over k pi, and the limit from 1.5 up to 2. Well, since I don't like negative sign, I will remove it and I will change the limits of integration. And I take 1 over k pi as a common thing. Then I have cosine k pi t, and the limit I flip. The price paying for the removing negative sign. Cosine k pi t over k pi. Integration. Okay. Now we'll start our business substitute and see when it's 0, when it's 1. Cosine, first I put cosine 0 minus cosine, that's half pi over 2 k. And let's continue, plus I put 1.5, 3 over 2. So I have cosine 3 pi over 2k. Because I'm substituting by t, not k. All right, just was also when I was sitting, I said, okay, we're doing k or t? No, t, because we're integrating with this with t. Minus, I put t equal 2, so you have 2 pi k. Here you go. That's what we have. We'll look for each term. Cosine 0 is equal 1. Minus cosine pi over 2k, that has issues. When you put k equal 1, you get cosine pi over 2 is 0. When you be opposite of sign, when you put k equal 2, you get cosine pi negative 1. When you put k equal 3, you get 0 again. When you put k equal 4, 4 over 2 is equal 2 will be cosine 2 pi, right? But it's equal 1. So I can say that this term, cosine pi over 2k, only an even. So I'll write when k equal 2, that will be equal to, the value will be equal to negative 1. When k equal 4, just something to remind me, equal positive 1. Plus, the same issue will happen with this one. Let's see, cosine 3 pi k over 2. Let me see, when k equal 1, you get cosine 3 pi over 2. That's 0. Once you have 2 on the bottom, for cosine is 0. Why? Because cosine pi over 2 is equal to 0. That's why. When you put k equal 2, 2 cancel with 2, you have 3 pi. What's 3 pi? 0, pi, 2 pi, 3 pi. If subtract 2 pi, be negative 1. Okay. So it'll be just the same, right? It will be the same. Oh, no, cosine 3 pi is equal 2 pi over pi. Yes, negative 1. It's the same. So let me write here. And I write the same thing. When k equal 2 was equal negative 1. When k equal 4, it's equal positive 1. Just to remember. The last one, 2 by k. There is no 2, so that'll be easy. You put k equal 1, that will be 2 pi. That's equal to 1. You put k equal 2, 4 pi. It's equal always 1. Always equal to 1. Good. So what you have, 1 cancel with negative 1. And these terms are equal. Equal, right? But there's one in the front of it negative. So when this one negative 1 and this negative 1, negative times negative will be positive. So the whole thing will cancel with this one. It's equal 0. Very interesting. We are going, a property we are going to learn what happened when the function or the signal is even or odd. And then we'll learn if the function is even, bk is equal 0. But I did that intentionally just because I want to practice how to do bk. But I mean, if I know that this is even, I don't have to waste my time in it. When it's even, bk is equal 0. It means I don't have sine terms. I have only cosine terms. So let me write now. We got ak and bk is equal 0. Now I just can write bk is equal 0. The question is now how I use the all coefficient. Well, now I'll write x of t equal a naught. We found a naught equal to what? I have it in the paper. One half, that's right. So x, oh, let's change the color. All right. So x of t, the square wave, will be equivalent to what I'm going to write. 1/2 dc plus. Let us just choose like the first components. I have to go. So let me write for you. If you make the summation, and I will erase it. Summation from k equal 1 to infinity, ak cosine k omega naught t plus bk sine k omega naught t. We are lucky. bk is equal 0. We have only cosine terms. If you do that, you'll say 1/2 plus. Now you look for ak because we found ak is not there all the time. I think we found out that when it's odd, it's equal 0, right? Let me check, go back and see what we got. ak, yes, that's our ak. It's either equal positive 2 or negative 2, right? When k equal 1, 5, 9. So let's take, the first 3 terms. So what you're going to take? The first 1, 3, 5. Because if you order, no even. So you have 1, 3, 5, 7, 9. You can continue, right? Maybe somebody asked, okay, what about if I want to write the general formula? You can go ahead. That's your AK. So that's your AK, right? Let's do that. So I'll say the summation k equal 1 to infinity, and I put the AK, which is this big term, 1 over k pi sine pi over 2k. It's just hard to remember. Yes, and then the other one, negative 3 over 2. And by the way, there is a way that to make this look smaller. I did abbreviation for all this, and I make it down to AK is equal 1 over k sine k pi over 2. But I don't want to just make it like that because we're going to use numerical value. And time cosine k omega naught, you have to put pi. We got omega naught pi. Don't put omega naught, put the value t. And now, if you wish, you can use, let's say, the first 3 terms. We said that you can have 1, 3, 5. Let's stop at 5. Well, the first fundamental component, I put k equal 1. So when you get k equal 1, you'll have 1 over k equal 1 pi. And what's sine pi over 2? Yes.
Is that sine pi t over 2, or is that sine pi k over 2?
This one? Are you talking about this coefficient?
Yeah.
The coefficient is not variable of time. It's amplitude. So it's function of k only. So when you have k equal 1, what you get here? 1. And when we get 3 pi over 2, will be negative 1, will be 2. Okay. 2. So that's 2. I'm working with k equal 1, by the way. So I got to when k equal 1, the all coefficient here is equal to over pi. Cosine, put k equal 1, pi t. What I did, that's the fundamental component. So if you are asked what is the amplitude of the fundamental component and the frequency, you will say that the frequency of the fundamental component is pi radian per second. The amplitude of the fundamental component is equal to 2 over pi. Yes. That's, the formula. Here you go. That's the formula. AK cosine k omega naught t. But remember, your omega naught is equal pi. So I'm substituting by the omega, not by pi. And the same thing here also. If you have that this term exists, k pi t. That's the omega naught. AK, it does not have t. It's amplitude. It's a value. Okay. So when I substitute by k equal 1, I got 2, and you have 1 pi, so 2 over pi. So you can write that the amplitude of the first component, the fundamental, is equal 2 over pi. Let's take the second component. The second component is not going to be even, be odd, 3. right? We found that. So let's just find plus 1 over k pi. K is equal 3 now. So it would be 1 over 3 pi. What is the value of this one? We agreed that one time will be 2, one time will be negative 2. We did it before, so you have to save time. Negative 2. Cosine. K is equal 3. So 3 pi t. Let's simplify this. Negative 2 over 3 pi. Negative 2 over 3 pi. So negative 3 over 2 pi. And you can continue to find the fifth. We can do it easy. Fifth. Oh, yeah, flip it. You see? I mean, yes, you're right. Negative 2 over 3 pi. Because the top part always 2, negative 2. So what you observe, the second component is third harmonic. Why? Because the frequency 3 times the fundamental. So if you are asked what the third harmonic, it's the frequency equal to 3 pi, radian per second. What is the amplitude? Negative 2 over 3 pi. As amplitude, you can say it's 1/3 the amplitude of the fundamental. 1/3. It means if the fundamental was 30, that would be 10. It's 1/3. If you want to get the fifth, it's easy. Now it's easy. It'd be like easy. Fifth, you have 5 on the bottom, 2 on the top, because one time positive, one negative, and then cosine. You can just continue. I just took time in the first one, second one, just then you figure the pattern, you know. So you have k equal 5 pi t, and then you can continue. You can continue to infinity. If you're asked about the first 3 terms, that's it. So x of t, the square wave consists of these factors. And by the way, you see the fifth harmonic, the magnitude is 1/5 of the amplitude of the fundamental. Means if you have you have 1, if you have 1, so 1/5, like 20%. And if you go to 7, we 1/7, like that, decreasing, yes.
Okay, so the 1/2 is the average value. The 2 pi.
2 over pi.
2 over pi.
The amplitude of the fundamental.
Okay, so that one's going to be the first fundamental, and
yes,
the second fundamental is the.
No, we don't have something called second fundamental. You have only one fundamental.
Then what's the negative 2 over 3 pi?
That's the third harmonic.
Okay, so.
Why I call it third harmonic?
Because the second one was 0. The second
No,
harmonic.
I'm asking why I call this the third harmonic.
Because it was k equal 3.
Yes, because the frequency 3 pi, 3 times the fundamental frequency. The frequency of the third harmonic 3 times the frequency of the fundamental component. That's why I call the third harmonic. Yeah, it's ordered the second one, but I mean, I'm afraid to say second one means if you think that the frequency, the following components is the third harmonic. So that's how you do the Fourier series using trigonometric series. Of course, there are things that will help you, like I give you the table. I'm going to give you the table about it makes life easy. I'm giving the general expression, and when it's even function, you will find out that bk is equal 0. So when you look at the function first, look at the signal. Is it even or odd? If it's even, don't calculate, don't waste your time to find bk. And if it's odd, ak is equal 0. AK is equal 0. That's not necessary. It doesn't have to be. Could be 0, not 0. But AK is equal to 0 when it's odd. All right. So you always, I mean, put this in mind. You save your time when you know. And also, when you make the integration, you remember when if it's normal, not even, not odd, and you want to find AK or VK, you multiply the integration by 2 over t, right? Here, 2 over t. When it's even or odd, you are going to change this period. You are going to integrate over half period, and you multiply this 2 by 2 before over t. That's why I find 4 over t. And because it's symmetric, so you don't have to the whole period. Take the half period and double it because they are symmetric. The same thing will happen with the odd. So that's the only difference. But A naught, the same expression does not. Yeah.
How can we tell if it's even or odd?
Good. Okay, we did that in signal in the beginning, even an odd function. And even if you don't have an even function, we get the odd component. It's even when it's symmetric about the y-axis, like the one that we worked out, square wave. You see the same example. I mean, I did one time on homework that for one thing, the square wave. That square wave, that's even because you look at the y-axis, the one to the right and left, they are equal. Odd would be if you have like something like that. If you have square wave like that, let me show you. Now, when you look at this one, it's not symmetric here, but you have one reflection and another reflection. You get it in the bottom. That would be the odd. That's, I mean, how graphically you can tell. Mathematically, you can do this. The same check that we did in the beginning. If x of minus t or negative t equal x of t, it's even. If x minus t equal minus x of t, will be odd. So that's, I mean, how we do it algebraically, and we did that in the first chapter for even and odd function, and that will make your life easy. I give you an example. That's an even function, symmetric about y-axis, and this one symmetric about the origin. That will be the odd. Do reflection. If you make reflection on the y-axis and then again on x-axis, you get that's the odd function. So that's how you do that. There's no time for quiz.
Thank God.
Well, I will do quiz. I mean, they can do it at home, not today, till you study the material. I'm going to upload this one. I think even I uploaded the material. So, yeah, I did. So, do you have any question? You will have. You see, the only thing to do, you got to practice. Okay, I'm going to upload the folio with the integration table. Simple. I'm going to just tell you now. Maximum, you're going to get something like constant multiply, because the problem, any function multiplied by sine and cosine. So what you got to know the integration of sine by itself, the integration of cosine. Maybe I will have a straight line like sawtooth like that. So it means you want to have t times sine integration or t cosine. And the ultimate thing we're going to go e minus t times sine t, e minus t cosine t. I'm not getting like even x squared. These are the three things I'm going to limit myself in this course, because I'm not going to test you in integration. And if there is something, I have to give you that for. Any question? No question. All right, let's move to another thing here. Important about sometimes when you read the expression for what's that? When we did, you see all the things. It's sometimes hard to read it. The people that they are interested in that, they said, okay, why we don't do something like some kind of graph to tell me? Because what you are interested in, you are interested in something called the magnitude and the shift of the angle of each component. You want to know, because when you analyze the circuit, you know what's the amplitude of this component and what's the phase shift. Right now, I'm not going to show the phase shift, but at least I will show you the magnitude. If you want to make something called line spectrum, you just make like graph and look at the amplitude 2 over pi, half, remember this number, minus 2 over 3 pi, 2 over 5 pi. So we do something called line spectrum. You put the frequency here, F or omega. When you have omega is equal 0, it means the DC component, right? It was half. So you put one line at half. Then the fundamental component, the frequency was equal to pi. So I'm using actually now omega, pi. It was like 2 over pi. What's 2 over pi? 2 over pi. Pi is almost equal 3. So it'll be like 2 over 3.67. That's a little bit higher than the DC. So 2 over pi. That's the first one. Well, 2 pi, nothing. 0. We don't have even. The third, we have the third. It was like this divided by 3. So it's easy. 1, 2, 3. So 1/3. Be like that. Which is equal. Oh, but that's negative. It was negative, right? So it was negative or positive?
Negative.
Negative.
That
Okay.
was, that was the -2/3 pi, right?
Oh, yeah. So you have to make it by the sign. So by the negative, smaller, actually. It's 1/3 of this one. 1, 2, 3, so something like that. Minus 2/3 pi. 4 pi is 0, 5 pi. It will be even 1/7 will be like that. So they like to look at this graph to know the magnitude. Just when you look at that line spectrum, so you can tell about the magnitude of each component. And if you are designing a filter, you say, okay, the filter here, I mean, you want the fundamental component. Okay, the third. So, okay, I'm going to get rid of the third, but I'm not going to design it over the 7 or the 9 because they're small. So I don't have to cost myself a lot of money because I mean, every time you design the filter to move many components, that would be expensive because the design will be complicated. The elements will be more complicated. So just to look for which one is big, really. So I see the third harmonic, the fifth, and I think 7th will be like vanished, like not effective. So I say, okay, I'll make filter, and this filter I'm going to design it in a way, the third and the fifth, and maybe the 7th. That's it, not more than that. So that they call it line spectrum, and we're going to explain more. I mean, because I didn't show you the shift, but I'm just showing one of the application that they do. Even the people that they are designing musical notes, things like that, they look at when they analyze things, then they see where they want to increase the tone, which tone. So, okay, go back and change the signal to increase some tone by increasing some frequency. And you can play with MATLAB and change the frequency and use the function echo and listen to it. You'll see the difference. Okay, I'm not going to give you a headache more than that. Okay, that's enough. Integration, things like that. But it's very important to practice for your series. And the topics who are getting every time is not going to be less than for your series. Just to be ready, I won't prepare you. So that does not be less than. Yeah, don't think it's going to lighten up. No, it's not. But it's not going to be difficult. It'll be the same level. All integration, things like that. And summation when we deal with the discrete time set. Any question?